Okay, hello. Hope everybody's surviving and staying healthy. Um, this is the test 4 review for Calculus 1, and I'm just going to go over it's purely computational. There's not really any theoretical stuff. It's more about just do you know how to integrate? That's the main question here. And so test 4, and we'll start with section 5.1. And my objective is just to go through each section and do some sample problems that will be similar to the kinds of problems that I'll put on the test. Okay. All right. So 5.1, we're looking at questions like 11 to 35 odd. And this is where we first introduced the idea of the integral as the antiderivative. And so let's look at a problem like number 12, or maybe even number 13, right? So 13, the integral of 1 all over x times the square root of x dx. Right? And the objective usually for these is to rewrite it and then apply maybe one of the simpler rules like the power rule. And so I'll rewrite this thing. And I note on the denominator here, x is really x to the 1, and the square root of x is really x to the 1/2. Right? And then you could use your properties of exponents to add 1 plus 1/2, right? If it have the same base, all you have to do is add the exponents. So if I had a to the x times a to the y, that's equal to a to the x plus y. Okay, so that's the idea here. Rewrite this as 1 all over x to the 2 halves, or 2 halves plus 1 halves is 3 halves dx. And then I'm going to rewrite this with a negative exponent, right? So our negative exponent rule says if I have 1 over a to the x, that's the same as a to the negative x. So I can rewrite this thing as the integral of x to the negative 3 halves dx. And then I can do the power rule. So I'm adding 1 to the old exponent. So I'll have x to the negative 3 halves plus 1, which is negative 1/2. And then I divide by negative 1/2. But I think it's easier just to think of multiply by the reciprocal. Okay, so this will be times negative 2, and then plus your integration constant, as usual. Generally, calc teachers want you to rewrite this without negative exponents. I don't really care very much, but if you get such a calc teacher in the future, you would probably have to rewrite it like this, or rewrite it with a square root. So negative 2 over square root x plus c. Okay? And that's probably the answer they have in the book as well. Let me check the answer just to make sure I've not done these ahead of time. Okay, so that looks good. All right, so in this section, we developed basic rules of integrals. You can pretty much integrate any polynomial, hopefully, that I throw at you. So, for example, number 19. Number 19 is a product of two factors inside the integral. You have this expression. And one thing you should learn about the integrals, it doesn't have like a square root property, right? The square root of a product is not equal to the product of the square roots. The integral of a product is not equal to the product of the integrals. Just like with derivatives, the derivative of a product is not in general equal to the product of the derivatives. So we can't just take the integral of this times the integral of this. No, you'd have to FOIL. Okay, so first we have 3x squared outer minus 2x inner plus 3x, and then last minus 2. That's all dx. And then combine your like terms if you didn't already. So we got the integral of 3x squared minus 2x plus 3x is plus 1x, and then minus 2. Okay, and then we should be able to integrate any polynomial I can create. So here you could leave the 3 alone. You'll have x to the 2 plus 1 is 3, and then divided by 3, or if you'd rather, times 1/3. Okay, I like to multiply by the reciprocal of the exponent, and that's just the way I do it. You could do it. You could always, write it out like literally x to the 2 plus 1 all over 2 plus 1. I've seen people do that times 3, and then, you know, simplify. But I just like to do it this way. Okay. So plus x, and so you go x squared times 1 over 2, and then minus 2x, and then add in your integration constant. So you'd have x cubed plus x squared over 2 minus 2x plus c. Don't forget that integration constant. The integral does not, it's representing a family of curves. It's not just one particular cubic. I'm just checking my answer. Okay, looks good. Alrighty then, let's see if we just do a couple more. Oh, 23 is definitely one that I like to annoy students with. 23. You have the integral of x plus 6 all over the square root of x dx. So how do we do this one? We're going to butterfly it. Okay, so we'll cut it up like that, and we'll have two integrals. So the integral of x over square root of x, which is the same as x to the 1/2, plus 6 over the square root of x, x to the 1/2. Okay, and then I'll use my power rules, my rules of exponents to reduce. So x to the 1 over x to the 1/2, you subtract the exponents, right? So you get x to the 1 minus 1/2, which is x to the 1/2, and then plus 6x to the negative 1/2. Okay. And then we need to add 1 to the old exponent and divide. So I'll get x to the 3/2 divided by 3/2, same as multiplying by 2/3, plus 6 times x now to the negative 1/2 plus 1 is 1/2, divided by 1/2 is the same as multiplying by 2, and then plus c. And then clean it up for me. Okay. And that should be your answer. Let me check, make sure I got it. Okay, great. All right, the next couple of problems, probably want to look at some trig versions. Okay, and I mentioned we're at problems 31, 11 to 35. Okay, we're good. All right, so let's look at, I guess, 27. You have the integral of secant squared theta minus sine theta d theta. So you need to have a lot memorized for doing integrals, but hopefully if you did a lot of derivatives, it's just doing the reverse, right? So if you know your trig derivatives, for example, the derivative of tan is secant squared, you know the integral of secant squared is tan. So I can think that way. The integral of secant squared is tan theta. And then the integral of sine is negative cosine, right? So we'd have minus negative cosine theta plus c, and then if you simplify, negative negative is positive, so I got tan theta plus cosine theta plus c. Okay, so no big deal there. Making sure my answer is correct. Tan theta, cosine theta plus c. Okay, we're good. The next one I put on my test like last year, and a lot of people dropped the ball on it. So I kind of expect you to know the basic, what they call Pythagorean identities. So if you've forgotten the basic Pythagorean identities, sine squared theta plus cosine squared theta is equal to 1. And then if you divide everything by sine squared, you get 1 plus cotan squared theta equals cosecant squared theta. And then if you divide the first equation by cosine squared, you get tan squared theta plus 1 equals secant squared theta. Okay, so I expect everybody to kind of know those, and if you see that identity, if you got it really encoded in your brain well, you can kind of see, all right, that's just secant squared, and I could rewrite this as the integral of secant squared y dy, and then from before I know the integral of secant squared is tan, so my answer must just be tan y plus c. Okay, so every once in a while you'll be called upon to do some trig identities. Not a lot of them though. Okay, I don't expect anybody to remember the crazy ones. I don't even remember them. But anyways, let's move on. What else we got? Some exponentials, right? Select number 31. The integral of 2 sine x minus 5 e to the x dx. Okay. Exponential is one of the easiest integrals. It is what it is, right? So integral of 2 sine x, integral of sine is negative cosine x. And then minus 5, the integral of e to the x, just e to the x. Don't forget plus c. Okay. So you get negative 2 cosine x minus 5 e to the x plus c. Please don't write this without parentheses. You have to have those parentheses, or it looks like you're writing 2 minus cosine x. You may know what you mean, but I'm not going to know what you mean, and that's a big problem. Okay, communication's so important, right? All right, so just make sure you're being careful. Last sort of important integral in this section is the natural log integral. So 35, the integral of x minus 5 over x dx. And so what we get there is x squared over 2 minus 5 times the integral of 1 over x, which is the natural log of the absolute value of x plus c. Okay. It just comes down to experience and doing tons and tons of integrals. My first job was grading for Calc 2. I would grade like 4 sections of Calc 2. This is before they had like computer graded software and stuff, and I would literally sit there and grade hundreds of papers a night, and all I did was integrals. So literally tens and thousands of integrals. I've done more integrals than anybody should have had to ever do, but oh well, I got paid for it, so I'm okay. But anyways, it's experience. You're basically training your brain to kind of learn something, just in the same way you learned how to do addition back in the day. So in my classes, I usually advise people to make flashcards. It's sad that we couldn't meet in person, so I could kind of remind you every day, make flashcards. Okay. Anyways, that's 5.1. 5.2. We have problems like 29 to 33 odd. So this is where we're developing the kind of functionality of the integral. And later on, you get tons and tons of different versions of the integral to do various things. So you'll want the integral to find properties from physics, like things like, I don't know, center of mass and volume, well, obvious ones like that, things like that. And you'll develop the integral, the insides of the integrals, to do all these different things. So yeah, if you're good with the foundations of these integrals, and we get later and we start throwing tons of different weird integrals at you, it'll be easier to stomach. Okay, and that's the only reason why we kind of harass you. But I know not everybody is going on to bigger, better calculuses, so I'm not going to harp too much on this. I just want to look at maybe a couple approximation problems that get the kind of idea of where the integral is coming from. So it's about finding area underneath a curve, and then finally taking the limit. So it is, you know, essentially a limit process. But anyways, 5.2, and I got to toggle over in my ebook, so just bear with me. 5.2, we're talking about the area underneath the curve. The area problem actually came before the derivative problem. It goes back to the Greeks, I think. Okay, so 5.2, where are we? Number 29. So we're approximating the area of a plane region. We're using left and right endpoints to do these. So, you know, problem like number, let's do 33. So we have, well, okay, sure, why not? So we have f of x equals cosine x, and the interval is from 0 to pi over 2, and we want 4 rectangles for our approximation. Usually what I like to do is take that interval and section it up right off the bat. So I got 0, here's pi over 2, and basically you need 4 gaps inside of this interval for these 4 rectangles to exist over top. Okay, so there's 1, there's 2, there's 3, there's 4, right? 1, 2, 3, 4. To get the length of each particular subinterval, what you do is take the length of this interval, which is pi over 2 minus 0, and then divide by 4. This is the famous b minus a all over n formula, which is change in x. Okay? So anyways, this is pi over 2 basically divided by 4, which is the same as multiplying by 1/4. And so that'll be pi over 8. Okay? So these points here, 1 pi over 8, 2 pi over 8, 3 pi over 8, and then 4 pi over 8 is pi over 2. Okay, so we want to do 2 different approximations for the area underneath this curve from 0 to pi over 2. And you kind of know what the picture is, right? It's looking like this, sort of. It has that shape. And so for the right endpoints, what we're doing are picking out these rectangles based off of the right endpoint. Okay, so this rectangle, where the top of the rectangle, the right top part of the rectangle touches the curve. Okay, the right top part touches the curve. And this one will just be 0 apparently. Okay, and then what you do is add up the area of those rectangles, and that's one approximation. So using the right endpoints, you should have 4 terms in your sum. Okay, so you'll have f of pi over 8 times pi over 8 plus f of 2 pi over 8 times pi over 8 plus f of 3 pi over 8 times pi over 8 plus f of pi over 2, which will be 0, times pi over 8. Okay? And you're plugging all this stuff into this function right here. Right? So this should, you could factor out the pi over 8. There's a pi over 8 factor in each term, so you could say this is the same as pi over 8 times sine, or it's cosine, so cosine of pi over 8 plus cosine of 2 pi over 8 plus cosine of 3 pi over 8 plus cosine of 4 pi over 8, which is pi over 2. Okay, and then you just plop that into your calculator and get your approximation. And that's one answer. So let me zip over to my calculator, make sure you're in radians. Pi over 8 times cosine of pi 8 plus cosine of 2, whoops, cosine of, come on, cosine of 2 pi over 8 plus cosine of 3 pi over 8, of course, plus cosine of the 4 pi over 8. That's the last one. Press enter, and I'm getting approximately 0.791 to 3 decimals. Okay, I'm just making sure I'm in radians really quick. Yeah, I'm in radians. Okay, I'm good. Okay, so that's the right endpoints. The left endpoints then, for your rectangles, you're choosing, well, guess what? The other one, right? And I don't have a different colored pen. That's why I'm freaking out here. Okay, so the green pen. This time, sorry, for the left endpoints, you're picking this point to figure out the top of your rectangle. So that would be right there for the first one. And then the second one, you're using this point for the top of your rectangle. And then you're using this point for the top of your rectangle, and then this point. Okay, so that corresponds to this for your f values. Right. So your left is going to be f of 0 times pi over 8. Let's just factor the pi over 8 out. Well, oh sure, let's put it in there. What the heck? Okay, and then plus f of pi over 8 times pi over 8 plus f of 2 pi over 8 times pi over 8 plus f of 3 pi over 8 times pi over 8. Okay. And then what do we get? So you can factor out the pi over 8, and you'll be left with cosine of 0 plus cosine of pi over 8 plus cosine of 2 pi over 8 plus cosine of 3 pi over 8. Okay. And then you plop all that junk into your calculator and get your answer. Okay. And it should be close to this other answer, you know, within reasons, within a reasonable margin of error. Plus cosine of pi over 8 plus cosine of 2 pi over 8 plus cosine of 3 pi over 8, in parentheses, push enter, and I'm getting about 1.183 to 3 decimals. Let me just get a check and see if that's 1.183 and point. Okay, so we're good. Right. So just, you know, later on you'll kind of, I believe in general, most of the integrals you're not going to be able to kind of find antiderivatives for, and you end up having to do like a numerical analysis type thing. So this kind of follows along. There'll be different kinds of problems in numerical analysis where you're doing Simpson's rule, the trapezoid rules, and basically you have different tops. So you can actually have like a trapezoid top. We're not going to do that here. Maybe in Calc 2 you'll do that. You can have polynomial tops, okay, and each sort of top gives you a different type of approximation, and sometimes the better tops give you better approximations. Okay. Okay. So that's 5.2. I'm not going to harass you with 5.3 stuff, even though I think it's important and definitely a great skill to have. Let's just move on to 5.4. So doing more integrals. All right. So let's see what I got. 5.4, I'm looking at questions like 9 to 33 odd. Okay, and I think this was the first fundamental, the first and second fundamental theorem of calculus. Basically, you can evaluate a definite integral by just evaluating at the limit points of the integral. Evaluate the antiderivative at the limit points. So, heavy theoretical stuff. Ultimately, okay, all I care about is questions 9 to 33. All right, so let's take a look at number 11. Okay, so 11, I have the integral of 2t minus 1 squared from 0 to 1. Okay, so you need to find the antiderivative first, and this is with respect to t. So I have the integral of, and I'm going to have to FOIL this out at this point. So I have 4t squared minus 2t is minus 4t plus 1, and then dt from 0 to 1. I have a polynomial, so we're doing power rule. So this first one, t cubed over 3, so 4t cubed over 3, minus 4t squared over 2, and then plus t, evaluated from 0 to 1. Okay. So plug in 1, and for wherever you see t, you'll get 4/3 minus 4/2, which is the same as 2, plus 1. And then minus, if you plug in 0, this will be 0 minus 0 plus 0, which is just 0. Okay, so we just have to add these up. Okay, find a common denominator, or I guess of 3. So minus 6/3 plus 3/3. And then we get 7/3 minus 6/3 is 1/3. Okay, and that should be our answer. Let me look. Yes, sir. Okay, let's do another one. Let's try, I don't know, 15 looks annoying. Okay. So 15, we have the integral from 1 to 4 of u minus 2 all over the square root of u du. Okay, so I looked at one of these earlier, similar to it, and what we did there was to fillet it or butterfly it, whatever you want to call it. And so what do we end up getting? U over square root of u is u to the 1/2, and then minus 2 over square root of u, which is 2u to the negative 1/2. And we're integrating from 1 to 4. Whoops, I didn't integrate yet. That's a boo-boo. Okay, so du. Integrate, get the antiderivative. So u to the 1/2 plus 1 is u to the 3/2. Then divided by 3/2, same as multiplying by 2/3. Minus 2. U to the negative 1/2 plus 1 is the same as u to the 1/2. Divided by 1/2 is the same as multiplying by 2. And then I can go ahead and evaluate. Please don't be creative with your notation. Okay, this is standard notation that everybody uses. So I see some people will put the bracket backwards or something for fun, and don't do that. Okay. All right. So now I want to plug these values into here. This is the fundamental theorem of calculus says we can do that. So if you plug 4 into u, well, maybe you've forgotten, how do we get 4 to the 3/2? That's the same as 4 to the 1/2 cubed, right? And then 4 to the 1/2 is just 2. 2 cubed is 8. Okay, so when I put 4 into here, I'll have 8. So it's 2/3 times 8. Minus 2 times 2 is 4. And then times u, 4 to the 1/2 is 2. Minus. Now I'm going to plug 1 in for u in both cases. And don't forget your parentheses. You have to distribute this negative to both terms. So I'll have 2/3 times 1 to any power is 1, so it's just 2/3, minus 4 times 1 to any power is just 1, so 4 times 1 is 4. Okay. Start cleaning stuff up, so 2/3 times 8 is 16/3, minus 8 minus 2/3, so distribute that negative, please, and then plus 8. Looks like the 8s will nicely cancel out, and then 16/3 minus 2/3 is 14/3, and that is my answer. On the test, please, whoops, I screwed up. The answer is 2/3. So what did I do wrong? All right, let's go back and check. So I have negative 2u to the negative, that's fine. U to the 1/2 plus 1 is 3/2, divided by 3/2 is 2/3. U to the negative 1/2 plus 1 is 1/2, divided by 1/2, and multiplied by 2 is 4. So I'm plugging in 4 and 1, right? So plug in 4 to the 1/2 is 2, and then that's 8. 4 to the 1/2 is 2. 2 times 2 is 4, times 2 is another 8, minus 2/3 minus 4. So this is 16/3 minus 8 minus 2/3, which is 14/3. I don't see what I did wrong. I copied it wrong? What the heck? I apologize. This is what I get for not practicing first. 1/2 plus 2/2 is 3/2. Negative 1/2 plus 2/2 is 1/2. 16. Oh, that's a 4. That's not an 8. This is a 4 right here. I apologize. Oh, I totally... sorry. Screwed that up there. That's a 4. So those won't cancel out. But these will still be, yeah, 14/3. And then I have negative 8 plus 4. So it would be negative 4. I'm so sorry. 14/3 minus 12/3 is 2/3. Okay. All right, then. So it's 15. Let's maybe do, what are we for? 1 to 33-ish. See if they got any trig. The absolute volume ones, sure, we can take a look at one of those. So it's 21. Maybe we should try 22. All right, so the integral from 0 to 4 of x squared minus 4x plus 3 dx, but it's in an absolute value. Right? All right, so when you have that case, you basically are going to have to split out into two integrals. So note, what is the absolute value of x squared minus 4x plus 3, which is what's in here. I didn't draw that very well, but well, it's going to be one of two things, right? It's going to be negative parentheses x squared minus 4x plus 3 if something happens, and then it's going to be positive x squared minus 4x plus 3 if something else happens. So how do I know where this thing falls? And I can set it equal to 0 to kind of find the places where it hits the x-axis, right? So x squared minus 4x plus 3 is the same as x minus 3 times x minus 1. Set it equal to 0, so x is 3 and then x is 1. And you could do a number line kind of analysis. So 1 and 3, 1, 3. So when x is like 0, I'll have a negative times a negative, it'll be positive there. When x is 2, I'll have a negative times a positive, so it'll be negative there. And then when x is, say, 4, I'll have a positive times a positive, so it'll be positive there. So it's negative if you're in this interval. So if you're between, if x is between 1 and 3, whoops, I wrote that in the reverse order, 1 and 3. And then it's positive if it's in between negative infinity and 1, or x is greater than or equal to 3 but less than infinity, that sort of thing. Right, so with regards to this integral then, I'm going to need to split it, right? I'm going to need 3 integrals. What an annoyance. So I'll have to go from 0 to 1, and in that case it's the positive part, so x squared minus 4x plus 3 dx, and then plus the integral from 1 to 3 of the negative part, so negative x squared plus 4x minus 3 after I distribute the negative dx, and then finally the integral from 3 to 4 of x squared minus 4x plus 3. Okay. All right, so I got 3 integrals to do. Let's get them done. First guy, x cubed over 3 minus 4x squared over 2 is the same as 2x squared plus 3 from 0 to 1, and then plus this integral, so that would be negative x cubed over 3 plus 4x squared over 2 is 2x squared, and then minus 3x. This should be 3x over here as well, from 1 to 3. And then plus this other guy, which will be x cubed over 3 minus 2x squared plus 3x from 3 to the 4. Okay, what a nightmare. Right. So this will be 1/3 minus 2 plus 3. Then plus, if I plug in 3, I'll get 27/3, which is negative 9. Plus 9 times 2 is 18, minus 9, and then minus, when I plug in 1, I'll get negative 1/3 plus 2 minus 3. And then for this other part, I got to plug in 4 first, so 4 is 64/3, minus 16 times 2 is 32, and then plus 12, and then minus, ran out of room. Let's put 3 in there, so you get 27/3 is 9, minus 18 plus 9. Okay. Right, I'm just looking for cancellations. I don't see if there's anything nice. But I'll add up the thirds first, right? So there's 1/3 there, 2/3 from there. So 66/3, which is the same as 22. So those are gone. And then all I have are constant, natural, or rather integer values. So 3 plus negative 2 is positive 1. And then I have, so plus 1. Negative 18 plus 18 is 0. I wonder if that works the same way down here, right? 18 minus 18 is 0. And then we have 2 minus 3 is -1, but then a negative 1 is +1. And then negative 32 plus 12 is negative 20. Okay, so we have 22, 23, 24 minus 20 equals 4. Okay. On my first job interview, I was tutoring online in calculus, and my interview, basically they gave me an integral just like that. Told me to do it, and then I got the job. Okay. Look. So anyways, there's that junk. There's also trig integrals in here. Let's just probably look at some of those. Let's look at number 25. So what do we got? 25, integral from 0 to the pi over 4, 1 minus sine squared theta all over cosine squared theta d theta. So again, I expect you to have memorized your Pythagorean identities. Trig stuff isn't going to go away in calculus. You'll have more and more trig on the horizon there if you take Calc 2. But anyways, I know this is true. And then if you move the sine squared over, you'll see that the numerator is just cosine squared. The numerator of the integrand is cosine squared. So this is just cosine squared. So I could rewrite this as cosine squared theta all over cosine squared theta d theta. And of course, that's just 1, right? So this is the integral of 1 d theta from 0 to the pi over 4. Integral of 1 is just theta from 0 to the pi over 4. And then plug in pi over 4 minus 0, and you just get pi over 4. Okay. Is that enough? Do we need one more? I suppose let's do one more. Let's try, I don't know, let's try 34. It looks vaguely interesting. So 34, the integral from e to 2e of the cosine of x minus 1 over x dx. Okay. The antiderivative of cosine is just sine, and then minus the integral of 1 over x is ln absolute value x. Okay. And then we have to evaluate from e to the 2e. Okay. So sine of 2e, I can't really simplify that. That is what it is. Minus ln of the absolute value of 2e is just 2e, so it's ln of 2e. And then minus sine of e minus ln of e. Right? Okay. So not much I could do with the sine junk. Sine 2e minus sine e. This thing right here is 1. Okay, so at least I could rewrite that. It'll be negative, so plus 1. This guy right here, you can kind of turn it into what? Well, I can say this is the same as negative ln 2 plus ln e, right? It's just the product rule for logarithms. If the log of a product is equal to the sum of the logs. Okay, so then ln e again, right? So I could rewrite that as just 1. So I'd have sine 2e minus sine of e plus 1. But then when I distribute this minus, it'll be minus 1. So the 1s will go away, and I'll just have minus ln 2 for my answer. Okay, let's call it quit on that stuff. Let's go to 5.5. And then we're 5.5 is all about u subs. So you need to master these u subs if you're going on. Very, very important process. So I'm looking at problems like 9 to 27 odd, 35 to 55 odd, 67 to 71 odd, and then 73 to 83 odd. Right? Okay, so let me scroll over in my book. To 5.5. Okay. Let's look at I guess number 17 is a good place to start. So I have t times the square root of t squared plus 2 dt. Okay. So you're looking to let u equal something such that when you take its derivative, you kind of see the pieces of it inside the integral. And certainly if I do u equals t squared plus 2, its derivative will cancel out this t here. So let's do that. U equals t squared plus 2, and then du equals 2t dt. And then solve, I like to solve for dt. Maybe the book does it a little different, but I'll have du all over 2t. Okay. So I substitute then this part, and I'll have the integral of t times the square root of u, and then I'm going to replace dt. dt is now du all over 2t. And it works if all the t material goes away, right? So this t definitely cancels with that, so we're good. I can factor out a constant of 1/2, so I do that as well. And I'm just left with the square root of u du, which we can integrate, right? So I'm going to rewrite it. It's the same as u to the 1/2. And then I can do a power rule. So u to the 1/2 plus 2/2 is 3/2. Divided by 3/2, same as multiplying by 2/3. Don't forget your integration constant. Sorry, I went off the page. Simplify, so you have 1/3. Back substitute as well. So u is t squared plus 2. And then it's to the 3/2 and plus c. Okay. Most everything else is just a variation on this theme. Let's look at 19. And what we have is 7x all over 1 minus x squared cubed dx. Okay, so a lot of the times whatever you see in the parentheses is what you want your u sub to be. But again, it's one of those things that just comes down to experience and doing hundreds and hundreds of integrals, making flashcards, that sort of thing. So u equals 1 minus x squared. Du is negative 2x dx. Okay. And then I like to solve for dx is negative du over 2x. Do my substitution. So I have the integral of 7x all over u cubed times dx, which is now negative du over 2x. Okay, and if we did it right, the x material should all go away, and certainly we see it going away. That cancels with that. The constant that I could pull out is negative 7/2, and then we're just left with the du over u cubed, which I'll have to rewrite. So this will be negative 7/2 times the integral of u to the negative 3 du. That'll be equal to negative 7/2 times, now I do a power rule, so u to the negative 3 plus 1 is negative 2, and times the reciprocal of negative 2. I usually just, if I'm dealing with negatives, I drop it to the denominator, so like that. And then we have to add in our constant. Let's clean it up a bit. So negative times negative is positive, 7/4, u to the negative 2 plus c. Let's clean it up a little bit at a time. I'm going to drop this to the denominator, so it would be 7 all over 4 u squared plus c. And then you always have to back substitute. So if you begin in x, you must end in x. So I have 7 all over 4 times 1 minus x squared squared plus your integration constant. Okay. Okay, so that's kind of the spielio. Let's take a look maybe at something more complicated. So 35 to 55. Is that any? Oh, these are trig integrals. Okay, sure. Let's look at 37. So that's definitely something we should know how to do. 37 cosine of 6x dx. Okay. You can always think of the antiderivative as kind of the reverse of doing the derivative. So in those regards, if you took the derivative of something like this, you'd end up having to do a chain rule. So multiply by 6. If you go in the other direction, so you take the antiderivative, you're going to end up dividing by 6. So very quickly, you could just say, oh, this is sine 6x. And then instead of doing the chain rule, where you multiply by 6, just divide by 6. Okay? If you don't like that, if you don't feel safe doing that, which by all means, I never did, do a u sub. So let u equal 6x. Okay? And then du will be 6 dx. And then dx, of course, just du over 6. Okay. So I can rewrite my integral now as cosine of u times dx, which is now du over 6. So there's a constant of 1/6 I'll pull out in front. Then I have the integral of cosine of u du. Okay. So that will be 1/6 times the integral of cosine u, which is just sine u. Let's see. And then back substitute. So you get 1/6 sine of 6x plus c, which of course is just what you got by kind of simply doing it. And I watch other professors at other schools teach this stuff, and what they teach is what I've seen other schools teach is kind of an educated guessing, where they'll train their students to kind of guess at the antiderivative, and then they just have to kind of even out, make sure they get the right constant for the cancellations, and you kind of can do that in your head by taking the derivative. So there's all kinds of different ways that they teach you to do these. At some schools, they'll have integral. What do they call, like you have a spelling bee? I've seen that at other schools. They'll have an integral spelling bee where they have students doing integrals in their heads in front of people and seeing who's the best at integrals. But I don't know how necessary that really is. I think it's a bit silly. Maybe a bit ostentatious, right? I don't know. Anyways, let's look at one with an exponential, I guess. Let's look at 47. And we have the integral of e to the x times e to the x plus 1 squared dx. Okay, so I'm going to let u equal the stuff in the parentheses just to see what happens, right? E to the x plus 1. So du is the derivative of e to the x plus 1 is e to the x plus 0 dx. And then I can replace dx with du over e to the x. Okay, so going back up to here, the integral of e to the x times u squared times dx, which is now du over e to the x. And again, if you did it right, all the x material will divide out, and you'll just be left with an integral in terms of u. And then you can integrate using power rules, so you get u cubed over 3 plus c. And then what do we have? E to the x plus 1 cubed all over 3. You back substitute, and that's your answer. Okay. Alrighty then, let's skip ahead. Sure, let's skip ahead. Let's skip ahead. So number 65 is definitely fundamental to your integral education. What do we have? 65. The integral of x times the square root of x plus 6 dx. Okay, I always put a variation of this on the test. You'll definitely see it. If you look at last year's test, I'm sure there's something like it on there. And why do I do that? It's because the traditional kind of substitution won't work, right? So you go to u is x plus 6, so du is just 1 dx. In other words, dx is du. So you could rewrite your integral x times the square root of u times dx, which is now du. And the problem is the x didn't cancel out, right? Oh my gosh, what am I going to do? Well, for this problem, you can actually not have to turn around and do a different sub. You can just sort of play around with that u expression. This is an equation. You can solve for x, right? So you could say, well, x must be equal to u minus 6. And then take that and replace this last x part with the u minus 6 expression, right? So this will be the integral of u minus 6 times square root of u, which is u to the 1/2. And then you could distribute you can't integrate at this point. You can't, like, the integral of a product is not the product of the integrals. Okay, so you have to distribute, and you get u to the 1 plus 1/2 is u to the 3/2 minus 6u to the 1/2 du. And then you could use a power rule. So you get u to the 3/2 plus 1 is the same as u to the 3/2 plus 2/2, which is 5/2 times 2/5. Minus 6u to the 1/2 plus 2/2 is 3/2 times 2/3 plus your integration constant. Then you have to back sub. So you'll end up with 2/5 times x plus 6 to the 5/2 minus 3 goes into 6 2 times. 2 times 2 is 4 times x plus 6 to the 3/2. And then again, don't forget your integration constant. Okay? Okay, so you'll definitely see one of those, and it's because it doesn't really fit. You know, it doesn't fit that kind of program I've been teaching you where you just substitute, make sure the stuff cancels, and you go from there. Right? No, there's not a cancellation, but it doesn't mean turn around and try a different substitution. We can actually just play around with this information to get a substitution. Okay? So sometimes you can think outside the box. It could be dangerous, but sometimes it works out, like in this one. Okay, so I expect to see one of those. Let's see, evaluating these guys. So let's try something like 75. Right, so we have the integral from 1 to 2 of 2x squared times the square root of x cubed plus 1 dx. Okay. So I'm going to do a substitution first, and you go like u equals x cubed plus 1. Okay. And then du equals 3x squared dx. So dx is going to be du all over 3x squared. Okay. And you could change the limits on the integral right now, or you can wait to the end and do a back substitution. Okay. So let's just go ahead and change them right now. So u of 2, the upper limit on the integral. If I plug 2 into this equation, it will be 9. So 2 cubed is 8 plus 1 is 9. And then for the lower limit, plugging 1 into there, 1 cubed is 1 plus 1 is 2. Okay, so my new integral will go from 2 to 9. And now I don't have to worry about back subbing once I'm done. Okay, so I'll have 2x squared times the square root of u times dx, which is now du over 3x squared. All the x squares cancel out, and you're left, you could pull out the constant factor of 2/3. The integral of square root of u is the same as u to the 1/2 du from 2 to the 9. Okay. And then we can integrate. So power rule, u to the 1/2 plus 1 is u to the 1/2 plus 2/2, which is u to the 3/2 times 2/3 in the front. And we evaluate from 2 to the 9. Then we have 4/9 times, plug 9 into there, 9 to the 3/2. What was that? That's the same as 9 to the 1/2 cubed. 9 to the 1/2 is just 3, and then 3 cubed, 3 times 3 is 9, times 3 is 27, minus, plug 2 into there, and that's not going to be so nice, right? That's just going to be 2 to the 3/2, whatever the heck that is. Okay? And I'm inclined to kind of just leave my answer that way. Let's make sure I didn't make a mistake. Usually they work out a lot nicer, right? Nope, I'm right. Okay. I guess that's good enough for that section. Let's move on to, well, let me cut the video right here so the video doesn't get too long. And then the next video I'll cover, looking for where I am in my notes. Oh, there I am. So I'm on, what section right now? I'm not even sure. I'm on 5.5. Yeah, so I'll cut the video here. In the next video, I'll catch up with 5.7, 5.8, and 5.9. Kind of let you know which formulas will be important, which you should have memorized. And okay, so I'll see you in the next video.